In this video, we're going to go over section 11.2 on series. So, if you consider a sequence an for an n equals 1 to infinity, and now you consider adding all those points, we get a series. So, because we have an infinite amount of points, we're essentially getting an infinite sum. So we have a1 plus a2 plus a3 up to an, and we continue adding and adding. This is what is called the infinite series. And you can denote it by this notation that we have with the sum or the sigma notation. And we can go from n equals 1 to infinity, or simply write it sigma an to represent the sum. Often we're going to be very interested in what is the partial sum of the series. And what you got to think about the partial sum is that essentially you're deciding up to where you're adding these numbers. So for example, if I do just s of 1, the partial sum of 1, it means that I'm only taking the first element of the sequence. If I'm doing the partial sum up to 3, I'm adding the first 3 elements of the sequence. And if I do, let's say k, the partial sum of k, then we're essentially adding the first k elements of the sequence. Now, it's going to be impossible to find a finite sum in general for the series. If we have something like 1 plus 2 plus 3 plus 4 plus n, is something that is just going to be keep adding and adding, and the sum is going to get increasingly larger. So this sum is probably going to go to infinity. However, that's not always the case. In some cases, you can actually find a finite sum. So for example, we have 1 half plus 1 over 4 plus 1 over 8 plus 1 over 16 plus 1 over 32, or the sum of 1 over 2n terms. That's something that you can't find a finite sum. Notice that if we start adding the first members of this, we get like 3 over 4. If we add the first 3 terms, we get 7 over 8. And in general, if we find the n first terms, we're going to find that this is like 1 minus 1 over 2 to the n. So this is actually telling me that it's very close to 1. So it's going to be bounded. The sum of this is going to be bounded. And if I keep going and going and going in terms, you can see that that's like taking the limit when it goes to infinity. And that sum would be the limit of this when it goes to infinity, and we actually get that this sum gets to be 1 at the end. Okay, so what happened is that those events gets placed to the definition of convergent and divergent series. As you can probably tell now, what we're doing with the partial sum is having a sequence. And when that sequence has a limit, has a finite limit that exists and is a real number, then the series is going to be called convergent. And we're going to be able to tell, oh, the sum of this an from n equals 1 to infinity is actually the limit of the partial sums, and is this number s. Now, in the opposite case, if the sequence of partial sum is divergent, then the series is going to be divergent as well. And in that case, well, the sum will go to infinity, or it will be a number that is impossible to calculate. So let's see an example of that. So given that we have a series so that the partial n sum is equals to 2n over 3n plus 5, then we can say, of course, we're going to apply the limit when it goes to infinity. The limit when it goes to infinity of this is going to be 2/3. And so hence, because that's representing the whole sum, then the series is going to be convergent, and the sum or the series from n equals 1 to infinity of an is going to be adding up to 2/3. One example of when that happens, and we can actually find out that partial sum of the n term is going to be the geometric series. The geometric series is a series from the type sum from n equals to 1 to infinity of a constant by a power r to the n. And this has the shape like a polynomial, and it's actually a polynomial if you open this up, and you can see this is a plus a times r plus ar squared plus ar cubed. And if you continue going, you can reach arn minus 1, so on and so forth. We're assuming, of course, that a here is going to be different from 0. And we're going to assume that r is going to be different from 1, because if r is just 1, we're just adding a infinite times, and the series is going to be divergent. However, if we have that r is different than 1, then we can just see the end sum as the sum of ar squared up to arn minus 1. Thanks to the shape of the geometric series, we can actually attempt to find what this is in a better expression. The way that we do this is we multiply by r everything. And so notice that r times s of n is ar plus ar squared plus ar cubed up to arn. And so now we can do the difference between Sn and Rsn. And when we do that, a lot of terms are going to cancel out, and I'm just going to have the first term and the last term. I'm just going to have left a and arn from subtracting these two. And so Sn minus Rsn is equals to a factor of 1 minus Rn. And now we can factor Sn here, and then we're going to have that the partial sum, the n partial sum for the geometric series is just going to be a times 1 minus Rn over 1 minus r. So because we now have an expression for the n partial sum, then we can attempt to actually take the limit. If we take the limit when n goes to infinity, everything is going to depend on the value of r. So if the value of r, the absolute value of r is less than 1, then the geometric series is going to be convergent, because this r to the n factor is going to go to 0, and everything is going to go to a over 1 minus r. Now, if r has an absolute value bigger than 1, then this is just going to be an exponential that is going to grow unbounded, and the limit is going to go to infinity. And so in that case, the series will be divergent. Now, let's take a look and check the convergency or divergency of a couple of examples. Notice that with geometric series, basically we only need to know if r is bigger than 1 or less than 1. Notice that in this scenario, we have 3 to the n over 2 to the n, which I can see as n equals 1 to infinity of 3 halves up to the n. And so this will mean that r is equals 3 halves, and so that is bigger than 1. So this is going to be divergent. Okay. Similarly, for the second series, we have 2 to the n over 7 to the n, but that can be seen as n equals 1 to infinity of 2 over 7 power to the n. And we know that this is just going to be the limit of the n partial sum, and the limit of the n partial sum is just going to be 2 over 7, a factor of 1 over 2 over 7 to the n minus 1. Over 1 minus 2 over 7. And so, of course, this piece goes to 0. And this is going to be left here 2 over 7. 1 minus 2 over 7. This is 7 over 7. Minus 2 over 7 is 5 over 7. So 2 over 7 over 5 over 7. This is just going to be 2 over 5. So we can actually, when it converges, we can actually even find out in this case how much is the sum, which is not going to be the rule. In general, you don't find how much is the sum, even if a series is convergent. Notice that in number 3, you also have a convergent series. This e to the minus n can be just rewritten as the sum from n equals 1 to infinity of 1 over e to the n. And since 1 over e is less than 1, then this can be just convergent. Now, the last two examples is the series from n equals 1 to n equals 1 to n squared. Those are not geometric series. So since they're not geometric series, I'm going to try and get something different for those. I'm going to define what is the partial sum. So notice that S of k is the sum from n equals 1 to k of n. And this is just the sum of the first k numbers. Luckily, we do have an expression for this. This ends up being k times k plus 1 divided by 2. But then notice that because we have that S of k is k plus 1 divided by 2, we know that the limit when k goes to infinity of S of k, which is the limit when k goes to infinity of k plus 1 over 2, this is just going to be infinity. There's no way to simplify this more. Okay. Now, the last one is going to be a similar situation. When we have the sum from n equals 1 to infinity of n squared. This is just like taking the limit when n goes to infinity. And we need to find out what is the sum of the first n squares. And so that's going to be n times n plus 1 times 2n plus 1 over 6. That's the sum of the first n squared. And so because this is also that sum, then this is going to be infinity. So we are in the same scenario as we were before.